Hi everybody. I just wanted to give you guys a quick introduction here to Chapter 8. So this is on sampling distributions. And so the main thing to keep in mind is that, in the past when we've drawn a sampling distribution, we've only drawn one. And so, but when you're doing a statistical analysis, right, depending on the sample that you draw, you may get slightly different values, right? So for example, if you're taking the sample of the height of everybody in Madison, for example, you're sampling it based on 10 people. If you draw a different sample of 10 people, you might get a different mean or something like that. So that's what we're going to be looking at. So in section 8.1, we'll look at the distribution of the sample mean. And these will be our objectives here: to describe the distribution of the sample mean using a normal population, and to describe the distribution of the sample mean using a non-normal population, right? So since our statistics now will have some variability to them, you can think of them as probability distributions. And there's an example of this on page 401, I guess. But so as I said before, statistics now, such as the mean, are random variables since their values will vary depending on the sample that you take. And so they'll have probability distributions associated with them. And so what we'll look at in this chapter is to focus on the shape, center, and spread of statistics, again, such as the mean or standard deviation. So the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from of sample size n, okay, so let's pick up where we left off here. So so the sampling distribution of the sample mean x bar is the probability distribution of all possible values of the random variable x bar computed from the sample size n from a population with mean mu, standard deviation of sigma. So as far as illustrating sample distributions, this is kind of the steps you want to take. Obtain a simple random sample size n, compute the sample mean. Assume we are sampling from a finite population. Repeat steps 1 and 2 until all simple random samples of size n have been obtained. And then that will be the procedure. So let's look at objective 1 here in describing the distribution of the sample mean with a normal population. The weights of pennies minted after 1982 are approximately normally distributed with a mean weight of about 2.46 grams and a standard deviation of 0.02 grams. Approximate the sample distribution of the sample mean by obtaining 200 simple random samples of size n equals 5 from this population. So the data on the following slide represents the sample means of the 200 simple random samples of size 5. So we're just taking the samples, and then these would be the means. So here's the means for 500 samples, or 200 samples. And so the mean of the 200 samples is 2.46, the same as the mean of the population. The standard deviation of the sample mean is 0.0086, which is smaller than the standard deviation of the population. And the next slide here shows the histogram of the sample means. So here's how the sample means are distributed. So one question is, what role does n, the sample size, play in the standard deviation of the distribution of the sample mean? And so what we'll see is, as the size of the sample increases, the standard deviation of the distribution of the sample mean decreases, right? Because as you're drawing larger and larger populations, it will get closer and closer to the actual value of the actual standard deviation, and so there won't be as much variation. And we'll see that the sample standard deviation, in this case of the variable x, will be the standard deviation of the population divided by the square root of n. So as n increases, that will decrease our standard deviation, or how much variability there is. So let's look at example 2 here. So let's approximate the sampling distribution using samples of size 20 in this case instead of samples of size 5. And so what you'll see then in this case is that the mean is still 2.46, but the standard deviation is now decreased to 0.0045, right? So the larger the sample is, the closer the sample size will be to the actual population, and the less variability there will be. So the mean and the standard deviation of the sampling distribution of x bar then is given by the following. The sampling distribution of x bar will have a mean of mu sub x, which will be equal to the standard the distribution of the population, and then standard deviation of the sample will be equal to the standard deviation of the population sigma divided by the square root of the sample size. X bar is called the standard error of the mean. The shape of the sampling distribution of x, if x is normal, if the underlying population is normal, then the distribution, if the sampling distribution will also be normally distributed. So we can use this information to answer certain questions, like, say, for example, what is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams. So you could plug that into your formula for calculate your z-score, again, because we're dealing with a normal distribution. That gives you a z-score of 0.79. And again, we're dealing with an at least situation here, so we want to take 1 minus 0.7852, and that will give you, and this 0.79 should correspond to that area. So take 1 minus 0.7852, and that will give you the area there in blue, which is about 21.48%. So there's about a 21.48% that the sample will have it be at least 2.465 grams. Objective 2 here then is to describe the distribution of the sample mean using a non-normal population. So we looked at a normal population, but let's say that the population isn't normal. Let's say it's a uniform distribution like this one, and we're just rolling a 6-sided die, so the probability that you'll roll any number 1 through 6 will be the same. Here's the mean and the standard deviation. So in this case, if you look at it, right, you'll see that the histogram for the sampling distribution is also approximately normal, right? It's not uniform like the original distribution, and you'll see that as n increases, that the distribution will become more and more normal. And this is brings us to what's known as the central limit theorem, which says that the shape of the distribution of the sample mean, so the shape of the samples that you're drawing from the population, becomes approximately normal as the sample size n increases, regardless of what the shape of the underlying distribution is, if it's normal or uniform or skewed left or right, etc. So let's look at an example here. So it says, suppose that the mean time for an oil change at a 10-minute oil change place is 11.4 minutes with a standard deviation of 3.2 minutes. A, if a simple random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. And B, if a random sample of 35 oil changes is selected, what is the probability that the mean oil change time is less than 11 minutes? So let's look at part A here first. So you would just take the standard deviation, which is 3.2, divide that by the square root of 35, which gives you 0.5409. And then for part B, again, you just take 11 minus 11.4 divided by the standard deviation, which is 0.5409, which we calculated in part A, and then calculate the corresponding probability for that, either in StatCrunch or looking it up, and you'll see that you get about 0.23 or 23%. Okay, well, I think that pretty much wraps up section 8.1. So the next thing we'll look at is the distribution of sample proportions rather than the sample mean. So we'll look at that in the next section. So like usual, if you guys have any questions about anything or whatever, just let me know.